up xy, and we slice through the cone. So if I'm doing dx dy, then I would slice perpendicular to the y-axis. And what kind of figures do we get when we slice the cone?
Hyperbolas.
Hyperbolas. Hyperbolas give us logarithms, and the logarithms have to disappear eventually, but that's what the 9 pages were all about. Now, what are the slices like when we're doing RD theta? Instead of a constant y, we're going to look at a constant theta. And so that means we're doing,
We're slicing it. Yeah.
and we're slicing it right up to the z-axis. So we're just getting triangles all the way around. So the geometry is different. Okay, so I wanted to do that one. I've already done problem 7.
Professor,
Yeah,
where does the minus a go on the, when you saw about the integrals, right?
yeah. Where does it go?
If you integrate it,
When I integrate it,
comes up.
So 0 to a.
so I'm going to get an r squared over 2. And so when I put in a, I'm going to get a squared over 2.
And isn't that after the r minus 1 over a r squared? Isn't that the form after you integrate?
This? No. That's the form after I multiply by r.
Oh, and factor out h, yeah.
And
Okay.
factor out the h.
Integrate that, you get 1 by 3a,
Uh-huh.
that's not cubed.
And it's r cubed. Yeah. So then I run 0 to a, and I get a squared over 2 minus 1 over 3a times a cubed, which gives me a squared
A squared.
times, what's 1/2 minus 1/3? Say 1/6.
1/6.
1/6. And so I've got this thing times what? H and 2 pi.
Oh.
You got it.
Okay.
Okay. I would like to look at problem 11.
Which supplement?
This is the supplement 8 with some impropers and some polars and all that stuff.
What supplement did you go to practice again?
What now? Okay, so the integral from 0 to infinity, the integral from negative x to infinity, and this is going to be, it's not x plus y this time, it's x squared plus y squared. And that right there suggests polar coordinates. Whereas the one I did earlier, polar coordinates probably wouldn't have been very helpful here. Anyway, this is to the 3/2 power. That's r squared plus 4. R squared plus 4. And we have a dx dy, or dy dx rather. And it just cries out for polar coordinates. I have 1 over r squared plus 4 to the 3/2 power. Notice that's really 3rd degree. And 3rd degree, and the top, of course, is 0th degree. So the discrepancy is 3, which is more than 2. As long as the discrepancy is more than 2, the infinities don't bother me. Now, if 4 hadn't been here, the 0 at the origin would have bothered me. That would cause divergence. But with the 4 here, it will not diverge. So I guess it will not diverge. All right. RD theta. And again, I'd have had to do a tangent substitution if I had not converted to polar. But as it is, I don't need a tangent substitution because I've got that r right here. And so let's see. Theta goes where?
Theta.
Limits from
It
theta?
goes on the outside, and it's 0 to 2 pi.
But x is positive.
It's from 0 to pi. No. It's from a negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. You sure about that this time?
One of those is positive.
In order to change from one setup to another, one coordinate system to another, and figuring out limits, you really need a picture. So let's draw the picture for this region. I've got x equals 0. And x goes to infinity. Ooh. To infinity and beyond. And so then let's see. And y goes to infinity and beyond. And what about the other end? Y equals negative x. I don't care about this part of y equals negative x, but I do care about this part. So we're going, if I look at a typical x coordinate, we're going from negative x, y equals negative x, all the way up there. So that's my lower boundary. You really don't want to try to set up intervals without a picture.
Oh, I can see it. It's going to cut right down the middle, so it's going to be like negative pi over 4 to pi over 2.
Mm-hmm. And then I look at some typical theta coordinate in between. Doesn't matter whether it's negative or positive, but it's going to start at
0 and go to infinity.
All right. And we can then separate this as usual, and we can do an r squared plus 4 equals u type substitution.
What would happen if you tried to simplify the denominator?
Simplified how?
Oh, never mind, I was thinking of r squared minus 4.
Oh, you're thinking r squared. Oh, so you're thinking factor.
Yes, I was thinking about that.
And that would give you r equals 2 being a bad point. If this was a minus, then you wouldn't want r equals 2, and this thing would have a whole circle's worth of divergence. Okay. All right. They have some problems like number 12 and 13 in the book. So I thought I would put one of these in here. So number 12, I've got the double integral over some region called P, 2 over y dA. And instead of giving you the boundaries in rectangular coordinates, here I'm giving you the boundaries in polar coordinates. I'm going to say that P is the region where you got this boundary, r equals sine 3 theta. So remember in chapter 10 of Calculus 2, once they start doing polar coordinates, or wherever else you did polar coordinates, like pre-cal maybe, you had to graph polar equations. And so this one, you could use your calculator and get this thing here, known as the three-leaved rose. And P doesn't stand for polar, it stands for petal. The rose here has 3 petals. Now, roses, the petals overlap each other, but that's not the case here. And let's see, I think maybe I got a little overboard on this one. RP stands for propeller. Whatever. So anyhow, it says the first quadrant region bounded by this graph. Good old first quadrant. So I'm just concerned with this thing. And so the integral, and you know, I'm either going to have to convert this to rectangular, which is really grotesque. I've done this for the rows with sine of 2 theta, and that's pretty bad. 3 theta, I've never tried it, but I think it would be 9 degrees. 9 pages, 93, whatever. So anyhow, either I have to convert this to rectangular, and we're not going to go there, or I've got to convert this to polar. Well, that's not too tough. That's just, what, r sine theta. And this is not too tough. That's just r d theta.
Oh, look, R's gone.
Oh, look, the r. We will regret its passing.
2 times cosine.
2 times the cosecant. Well, anyway, no big deal. Good thing we get to do the dr first. But anyway, so what are our limits?
It's going to be 0 to pi over 2.
0 to pi over 2. And then we would have from, you know, typical theta coordinate,
Sine 3 theta.
sine 3 theta on the top.
And 0 theta.
It starts at the origin and goes outwards. Now, it's not quite right. And partly that's because I didn't draw the picture that well. But when you think about it, if I do the sine of 3 theta, if I start at 0, I get 0. What about if I go around to pi over 6? If I go around to pi over 6. If I go to pi over 6, then I've got 3 times pi over 6, that's pi over 2. So that's going to go out to 1. If this is 1, then at pi over 6, I get 1. So it's doing this kind of thing. Now actually, I don't think I got pi over 6, really should have gone a little. There we go. And then I get to pi over 4. 3 times pi over 4 is 135 degrees. The sine of 135 degrees is 1 over root 2, about 0.7. So at pi over 4, we're about here. And then what happens next? We get to pi over 3. At pi over 3, we get the sine of 3 times pi over 3. That's the sine of pi, which is 0. It's 0 to pi over 3. Because after that, it's going to go negative. See, these actually represent negative r coordinates when we're up there. And that's why I didn't put this into the other pebbles. So anyway, it's 0 to pi over 3. That's something you have to look out for. Now, I'm going to do my r interval first. And that's a real easy one. If I switched it around, if I did the theta first, then I'd have to do, I'd have to be looking at inverse sine to get the limits. So we don't want to do that. So anyway, I'm going to have 2 times or 2 over the sine of theta times r. And r goes from 0 to sine 3 theta. So all I got is the sine of 3 theta over the sine of theta. And now you kind of have to do a little trig. The triple angle formula, the dreaded triple angle formula.
I remember there was one,
I remember what it is. Ask me. 3 sine theta minus 4 times the sine cubed of theta. And I'll leave it to you to work that out if you want to, or just go look it up, or trust me. So anyway, that means it's real easy to divide by the sine of theta. So we'll get 3 minus 4 sine squared. And I'm going to say it's 7.
Oh, wait, it's not a factor of 5 or 2.
Yeah, so it's not exactly trivial, which is why I'm not going to do it. Okay,
Should have said it.
etc. I should do at least one example that does not include the origin. So therefore I will. Here's kind of a favorite example of mine. This is going to be a parabola. This is going to be a circle. This is going to be the circle of radius 2. Circle of radius square root of 2. I want that to be a 2. And my parabola is going to be y equals x squared. And so look, if I have 1 plus 1 is 2, then 1 could be 1 squared. So this point is 1, 1. Which in polar coordinates means that my upper limit is going to be what?
Polar coordinates.
What line goes through 1, 1? What angle does that make?
45.
45, okay. So anyhow, the other boundary here is y equals 0. And one reason I like this example is it makes me think of the favorite movie I never watched. Anyway, so I'm just going to set this one up. I'm not going to actually do the integral calculation itself. So anyhow, theta goes from 0 to pi over 4. And I haven't even written down a function yet. So consider it written. This would be r dr theta.
Which one was that one?
The squiggle?
No, the one problem itself.
Oh, I'm just,
Oh,
I'm not even sure it's on here. It might be on here. But
when you read it up.
it's just one I always go to because it illustrates so many things.
Sharp.
Sharks, for one thing, yes. Never saw the movie, never really wanted to. But anyway, so now I took a look at a typical theta coordinate between 0 and pi over 4. And so let's say I might want to take this typical theta coordinate. Okay. And what happens here, although the origin is a point on the boundary, it doesn't really count. Because that's all. It's only one point up until you get to there. And as long as you've got a continuous function, and of course I didn't write down what the function is, but as long as it's continuous, as long as it doesn't go to infinity there, then one point never makes a difference. So I'm going to disregard this and I'm going to say, well, it goes in right there. And it comes out over here. So I have to convert the parabola into polar coordinates for the lower limit. And I convert the circle into polar coordinates for the upper limit. I want to do the circle. I want to do the circle.
No.
Okay.
R squared equals 2.
R squared equals 2. So R is
Square root of 2.
Okay. And now I'm going to deal with the parabola. So it's y equals x squared. And let's see, x is r cosine theta, and y is r sine theta, and you just plug them in. So r sine theta equals r cosine theta squared. So tangent. Not quite. Not, well, okay, which one are we solving for? We're going to scratch this r, which leaves me an r over here, and so yes, I will be moving the c squared over here to the left.
Tangent
Tangent
over
secant.
cosecant.
Well, tangent, let's see, sine over
Or
cosine
tangent over
times the 1 over cosine, so tangent secant. Secant tangent, okay. And I have to admit, I prefer secant tangent myself. Because I always think it's kind of weird, this parabola, which you would think has nothing to do with the derivative of secant, but this parabola, its equation, r is the derivative of secant. But anyway, it goes down here,
That's pretty nifty.
and et cetera. Et cetera. The et cetera means go out and find a function.
Why too lazy?
Well. Now, let me show you one other situation where, well, that frequently arises, like in exams maybe. What if I'm dealing with, just a plain triangle? So this is this will be 45 degrees. Let's do 5 or 6. So this is going to be y equals x over root 3, whereas in my very first polar coordinate example I did y equals x times root 3. So 1 over root 3 is the tangent of 30 degrees. Anyway, let's take this to be y equals 2 maybe, and x equals 0. And I'm going to set this up in polar coordinates. And you might think, why would you set it up in polar coordinates? Because, I mean, there's no circles around. Why not? Okay. I can convert anything, any region at all, I can convert it to polar coordinates. And I'll give you a reason. I'll give you another reason. What if your region, what if your function is something like 1 over the square root of x squared plus y squared?
That would definitely be a lot easier.
It would definitely be a lot easier in public. Again, avoiding those standing substitutes.
Is it the natural log of all?
No,
Sure.
I'm sure.
Is it R?
Or is this is 1 over r times
R given
r d r d theta.
So it's R.
So when I integrate it, it'll be r. That's right. So anyhow, limits for theta.
Oh, didn't you just say it was
I just said, yeah.
5/3?
Well, 5/3 looks more like that.
Oh, yeah, you're right. 5/6.
5/6.
Dang it.
And then-
Or, you know, you could just actually convert it. R sine theta equals R cosine theta over root 3. The R's cancel. I've got sine over cosine, so I've got tangent theta equals 1 over root 3, 5/6.
2 pi/2, right?
The 5/2. And then 0, we're back to letting 0 get into our game again. 0 to whatever this is.
2.
Nope.
Dang it.
If that was a circle of radius 2, it would be 2. This is y equals
2 root 3.
2. Nope.
2 over sine.
That would just be this one right there, 2 over sine. Let's see. So what is,
That's square root of 5?
shouldn't it be 2 minus 3? What?
No.
Whenever I convert, like over here, I replace x with r cosine theta and y with r sine theta. So here, I'm just going to replace y with r sine theta. And so it's 2 over sine theta. Oh, is that what you said? I think it was what you said. R2 cosecant theta. I'm sorry, I was,
It's okay, I mumble sometimes.
so did I. So 2 cosecant theta. And so when I integrate the r part here, I'll get 2 cosecant theta, and that's an easy integral. There's no divergence problems at all. So I'll just say et cetera.
What's the integral of cosecant?
What now?
What's the integral of cosecant?
Natural log of
Minus the log of the cosecant plus the cotangent. Or you could say plus the log of
cosecant minus cotangent.
cosecant minus cotangent. Those are the same thing.
Because laws are weird.
Plus the log of cosecant minus cotangent.
Yeah, don't get that to distinction.
Ah, but there's no absolute value here.
But yeah, it's in, within.
All right, so when we're out there in the boonies, we might have to have absolute values.
Yeah, in this problem,
But in this problem, we don't need it.
everything's in the first.
Anyway, those two
And then
are equal.
for secant, it's secant plus tangent, right? Natural log of secant, tangent.
The integral of secant is the logarithm of secant plus tangent.
Right.
Why are these equal?
Mm-hmm.
It's really a Cal 1 question, but it always fascinates me.
Oh, you factor out a -1.
No, you can't.
If you were to raise it to the power of -1, you just pull it out.
Okay, that's right. So I could take this minus and push it in here as an exponent.
Then it
My-
gets nasty.
No, it's not nasty at all. My favorite way is just move this over here to the left. So I've got log,
Clever.
cosecant. Well, they both start with C, don't they? And actually, I don't need that. I'll just multiply.
Difference of squares.
So I get the difference of squares.
Cosecant
Cosecant
squared
squared
plus cotangent
Minus cotangent squared, which is
I don't know.
cosecant squared minus cotangent squared.
Is that an identity? Like
It is an identity.
Is it 1?
It's 1.
Oh,
Because this is 1 over sine squared minus cosine squared over sine squared. Well, 1 minus cosine squared is sine squared, so I get sine squared over sine squared is
Oh, it's sick.
1. Yeah, I guess so. And the logarithm of 1 is
0.
0. So when I push this over here, I get this plus that equals 0.
that's a lot easier than
moving the exponent.
Yes, I think so. Now, which one of these is better? Which one of these is more honest?
The,
The one on the right.
The one on the right is more honest. Why?
Isn't that just the identity or?
Well, yeah, but I mean, why is this a preferable way to write it? In spite of what many calculus books have done. There's this one over there that says, look at me, I'm positive. But it's a lie. This is negative. Look, cosecant is greater than 1. Cotangent is greater than 0. Well, in the first quadrant anyway. So that's going to be something bigger than 1. So I get the logarithm of something bigger than 1, which is positive. The minus on it, you got a negative. So this plus here is really dishonest. Now, I think I've gotten into Cal 1 mode now, so I want to push on here. But anyhow, I wanted to show you several possibilities for the way the limits work out in polar coordinates. And straight lines, horizontal and vertical lines, show up a lot. And let's see, the horizontal line gives you cosecant. What do you think the vertical line gives you? Nope.
Or, secant.
Secant. Work it out. Okay.